Hello class, and welcome to today's lesson on the limits of infinite sequences. We've talked about finite sequences, but not really infinite sequences. So we're going to talk about that, especially with regards to limits. So let's do a quick reminder, and we'll do that with this question here, finding the limit as x approaches positive infinity for the function f of x equals 1 over x. So take a moment and try that on your own now. Alrighty, so when you begin this, first off, there's two ways of doing this. You can end up graphing this function, right, and looking at how it looks when you're approaching positive infinity. As a reminder, you have the vertical asymptote where x equals 0, and on the positive side, you're going to have a positive answer, so you have this approaching here, and on the negative side of it, you're going to have this approaching negative infinity here. And as you go larger and larger in the negative direction, you have a negative 0. So you're going to have a horizontal asymptote at 0 here, right? And on the right-hand side, as you approach positive infinity, you're going to get positive 0 here with a horizontal asymptote there. So you're approaching 0 here for x is equal to positive infinity. So let's do the limit, and actually do this limit notation. As x approaches positive infinity for 1 over x, you get 0. As a reminder, remember, it is approximately 0. We are saying in this case that we're going to have 0 positive. Okay? 0 positive here. Alright, so that's a reminder of what limits are. Let's get to the limit of something very similar. In this case, remember, an infinite sequence. So let's look at one. So for this given sequence, we're looking at it and we see that it's 1/2, 1/4, 1/8, 1/16. And I want you to try and find the change that's going on between these to make the next term. So the best way I would think to do that is to simply say, are we subtracting? Is there a common difference? And I'm going to say there's not, because 1/2 to 1/4, 1/8, it looks like to me there is a multiplication factor going on. And let's just check that out. I'm going to have 1/4 divided by 1/2. Do my weird method here. You're going to get 2 over 1/4, which is 1/2. You get this here, and let's check that for 1/8 divided by 1/4. Yeah, you're going to get again 4 over 8, which is again 1/2. So in this case here, yeah, we have a common ratio, r being 1/2. Well, what would be the explicit definition? For this one here, if I'm looking for any term, I'm thinking this one here is going to be 1/2. Well, that's 1/2 raised to the 1. That's the same thing. Here, well, it's going to be 1/2, but squared, because the numerator doesn't matter. It's always 1. The denominator is what's changing. So we have to have them keep multiplying, and I see this. So that's 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, so on and so forth, infinitely, because this is an infinite sequence because of the dot, dot, dot. So my explicit definition is going to simply be 1/2 raised to the n. Alright, so with that, I'm actually going to do something else with this. I'm going to decide to graph it a little bit. Just do a little quick sketch. So I'm going to start off with this being 0, with my y-axis representing my output, or my terms here. So this is going to represent my n's, right, my x-axis. Okay, I'm going to do that one and make it space equally. 1, 2, 3, 4, 5, 6. And in this case, I'm doing this, when I plug in 1, I'm going to get 1/2. So let's make this 1 here. Well, 1/2 is going to be halfway. 2 is going to be 1/4, which is a half of a half, and this one's going to be 1/2 of a quarter, so this is consistently half the distance up. And if you note what's going on here, as I'm approaching infinity, I'm starting to approach more and more a lower value. What value is that? Well, 0. So if this is a function, if I were to ask you, well, what is this sequence here? What is this sequence approaching as we go down and down, down, right? Well, I think you have a pretty safe idea to say it approaches 0, which it makes sense. I mean, if we have this as our explicit here, right, 1/2 raised to the n, the numerator is 1, so that's always 1. No matter how many times this can be infinite, it doesn't matter. But the denominator gets larger and larger and larger and larger and larger. So over time, it becomes a huge number. And when you divide by a huge number, you get approximately 0, right? So as a reminder, let's bring up limits here. As the limit as x approaches positive infinity for 1/2 raised to the x, you get 0. And note it is a equal sign because remember, you're taking the limit. Whenever you have the limit, you are saying what is it approaching. So one thing I want to note here very specifically, we actually have this theorem that now states that if r, your common ratio, is less than 1, then the limit of your ratio approaching positive infinity raised to the n is equal to 0. So make sure you get that down in your notes. Okay, we're going to try to apply this now to a new question. So we have this question here saying finding the limit as n approaches positive infinity for n squared plus 1 over 2n squared minus 3n. So I want you to take this moment and try it out, and we'll go over it. So you might remember how to do this, where you end up applying this idea of that the limit as n approaches infinity, n squared plus 1 over 2n squared minus 3n, that in this case I'm just going to plug in infinity squared over, plus 1 over 2 infinity squared minus 3n, or 3 infinity. You have that, well, if you actually look at this and compare these terms, infinity squared compared to 1, oh my gosh, it's not even a comparison. Plus 1 means nothing. It's inconsequential to infinity squared, so that's out. That's gone. Here, if you look at negative 3 times infinity, well, compare that to 2 infinity squared. What's larger here? This means nothing in comparison to this. So this is changing what you're approaching as x approaches infinity more so than this. So in this case, again, that's also dropping out. And you're left with infinity squared over 2 infinity squared. And note here, we can also cancel these out because they're the same values over each other. And you're left with an equals of 1/2. And I write this all in terms of n because, again, this could have easily been a sequence. And I could have started plugging in each and every term and got out, if I plugged in 1 plus 1, that's 1 over 2, 1 squared, that's 1 minus 3, right? That's 2 minus 3. You're going to get negative 1. So it's going to be overall 1 over negative 1, you get negative 1. So that's your first term of a sequence. And you can just do it, let's just do one more, just for giggles. You're going to get 4 plus 1 over 2 to the multiplied by 4 minus 6. You're going to get 5, 8 minus 6, that's 5 halves. That's 5 halves. And as you keep going on, dot, 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 what do you approach? 1/2. You approach 1/2. Oh, that's the dot, dot, dot. That's what it represents. The dot, as infinite sequence, you're getting to 1/2. So that's really important to note. All right, let's try another one. So for this one, I want you to take a moment and try this. I want you to show and prove that the limit of x approaches infinity for the function 7n cubed over 4n squared minus 5 is equal to infinity. So take a moment and try to show that yourself on proving it that that is indeed true. Now I'm going to take another perspective for this and try to solve this from a different point of view and say, you want to look for maybe, if my other method hasn't been working, one other way of looking at it is by looking to try and say we're making a term here or any term cancel out to be 0. So I'm going to do that with the 5 here, okay? And I'll show you just how to do that in a second by saying I want to get rid of this n squared all around. So what I do here is I have this base, right? I'm going to say that as I do the limit, before I plug it in, x to positive infinity, I have 7n cubed over 4n squared minus 5. What I'm going to do here is I'm actually going to try and take out the n squared. What I mean is I'm going to divide each and every term in here by n squared. So if I divide the top by n squared, I'm going to get 7n, right? That the n squared cancels out only 2 of the n's and it's left with 1 remaining n. Well, if I do that for the bottom, 4 is remaining. But what happens to the 5? The 5 is divided by n squared. So what does that mean? What happens here is if I look at this over n squared, if I plug in positive infinity, let's do that right now, right? If I plug in positive infinity, I get 7 times infinity over 4 minus 5 infinity squared. What happens here is this, remember, a very large number, this becomes 0. So I'm left with 7 times infinity over 4, which, again, it's infinity. There's no changing the denominator, so we're just left with this being infinity. So we call that this now does equal infinity, but we also say the series diverges. And I keep saying series, I think, during this, and I meant sequence. But in this case, the sequence diverges, okay? All right, now this was a review on limits, but it was also a review on applying this to infinite sequences because, again, remember, infinite sequences can just be like a function. You can just graph the series of points and plug them in. All right, so I hope you enjoyed this lesson, and I hope, if anything, if you remember limits, this was a good review, and look forward to seeing you all next time. Take care.